Welcome to Wireless and IoT Security. In Chapter 5, we talk about how does WLANs work. In this chapter, we talk about the topologies of wireless LAN, the standard 802.11 standards, how do wireless access point and bridges work, how do we do wireless antennas and wireless site surveys. Wireless communication requires that device communicate over a common radio frequency. ISM is short for Industrial, Scientific, and Medical Band of the Unlicensed Wireless Spectrum. WLAN technology requires each device in the network to be tuned to a specific radio frequency within the ISM unlicensed spectrum. The ISM band is available for use with short-range wireless communication techniques such as in-person networks, PAN, WLAN, and wireless wide area networks or WWNs. ISM provides easy access to the wireless spectrum for innovators and product developers through access to unlicensed RF bands. Devices must comply with strict regulations. Developing products that use this band requires government approval. The ITU created the standards that specify the frequency of the band, the spectrum, the transmission power regulations, and other characteristics. Most wireless devices work within the 2.4 GHz band. Wi-Fi, Bluetooth, RFID, Zigbee, 6 low WPAN, and NFC communication all use this spectrum. Another popular worldwide unlicensed band is the 5 GHz, which has a bandwidth of 150 MHz, making it suitable for higher data communication. In February 2020, a new frequency band at 6 GHz was approved by the FCC. The 6 GHz band should improve connection reliability, speed, and spectrum efficiency and reduce interference. So these are the parts of a WLAN. You have a radio card, you have a station which is compliant with the 82.11 standard. Any station can be any 82.11 capable device, laptop, smartphone, tablet, plug-in card. If it's an endpoint, it's called a client station. You also have a access point, which is also a station. It serves as a central hub that communicates with all client stations within range. Any device that meets the following criteria can act as a wireless client. It contains a radio card or integrated transmit and receive uh, function, or not as TXRX. It contains an antenna. It operates under the 802.11 standards. A client station is configured to associate with an access point by creating a layer 2 connection. Every access point is identified by a service set identifier SSID. SSID is a configured name of the alphanumeric code. Basically, it is your Wi-Fi name. If multiple access points configured within the same SSID and if the correct security credentials supplied, client will be handed over the strongest signal. Access point must use different channels to avoid interference. Before a client can connect to an access point, it must detect the presence of access point. There are two ways to detect the presence. You have passive scanning and active scanning. In active scanning, client proactively scans the network by sending a probe first request. In passive scanning, client listens for a beacon, which an access point continually emits. When the client hears a beacon advertising and SSID, it selects that access point. In the AOS 2.0 standards, define four topologies called subsets. This defines how the Wi-Fi devices connect to each other. You have the BSS, which is the basic service set. You have ESS, external service set. You have IPSS, independent basic service set. You also have the MBSS, mesh basic service set. The 82.11 standards outlines the protocols, methods, and controls for building, operating, and communicating over WLANs. Protocol revisions were noted by letter qualifiers such as 82.11a, 82.11n, 82.11g, etc. Several of the revisions specify new frequencies, channels, or modulation techniques. Many Wi-Fi router manufacturers use an error designation to differentiate products and ensure device compatibility. There's a new Wi-Fi Alliance naming system. So Wi-Fi 1 is 82.11b. It uses the unregulated 2.4 GHz band. You also have the A, which operates on 5 GHz. In 2003, the 82.11g came out. It supports bandwidth up to 54 Mbps and utilizes the 2.4 GHz frequency band. So basically, it's a greater coverage of 82.1a, and it's also compatible with 82.1b. The 82.11n came out in 2009. Is operates with 2. Operates both 2.4 gigahertz and 5 gigahertz, and the maximum speed is up to 600 Mbps. In 2014, 82.11 AC came out, which is an extension of the 82.11n. It offers more channels and straight up to 1.3 gigabits throughput on the 5 GHz band. In 2019, 82.AX came out, which is known as a high efficiency wireless standard. It offers theoretical network speed up to 10 gigabytes and up to 12 gigabytes operates within the both 2.4 and 5 gigahertz bands. In 2020, the FCC added third band at 6 gigahertz, effectively quadrupling the total space out to traditional Wi-Fi. To use a new swath of airwaves, equipment will need to support a new Wi-Fi 6C chipset. If you have more spectrum of 200 MHz in the 6 GHz band to work over, so you will be able to support more fully utilized channels without having to share out of the spectrum. The potential for Wi-Fi 6C is tremendous, but it will require buying a new Wi-Fi routers and devices such as smartphones and smart TVs to be able to benefit from this advancement. What does it mean to be unlicensed band? One, users can operate without FCC license. You also have a narrowband and spread spectrum. The 2.5, the narrowband spectrum uses a little bit bandwidth by transmitting over a narrow beam of frequency. The spread spectrum is spread across the entire frequency space available. You also multipath radio waves reflect off certain materials and surfaces to result in multiple versions of the same radio waves bouncing on, known as multipath. So here's a how multipath work, right? So here's a transmitter. You have a direct wave that goes to the receiver and the building. Well, when it hits the building, it gets reflected back to the receiver. You have frequency hopping spread spectrum, FHSS. It works by transmitting data using a small carrier space in short bursts and then continuously changing or hopping to another frequency during transmission. You also have DSSS, is hopping, but it stays on a fixed channel, hopping within the frequency space on that channel. This is by using a technique called data encoding. What are wireless access points? It's a half duplex switch that contains a radio card and an antenna that can be tuned to one or more unlicensed radio frequencies. Different warps can operate on several channels within each frequency. Network designers configure warps to ensure that non-overlapping channel plans are used to avoid interference. So here's an example of how channels are not overlapping. So you have the 82 point in 40 megahertz channel 1, but same right here, but it's on 20 megahertz channel. So these are on different channels. So even though they are on channel right here, they're on channel 1, they're now overlapping. WAPs acts as a protocol on a network, typically on another physical medium such as a wired Ethernet. Uses RF signals uses RF signals as a carrier band frequency. Frequencies are assigned to 82.11 are the unlicensed bands at 2.4 and 5 GHz. WAP radio cards are configured to work one of these two unlicensed bands and on several channels, continuously transmitting beacons on the selected RF band and channel to advertise its presence and configuration to any client station in broadcast range. Client station listen for WAP beacons through passive active scanning. The W2 uses four-way handshake for association. It provides mechanism for association. It produces an encryption key used to read broadcast messages, which has encrypted WP2. So you have an access point and a client. The access point it creates announce and sends to the client. Client creates a key and it sends a S nonce and NIC to the access point. The access point creates a key. It creates a GTK and MIC, send it back to client. The client acknowledges, send it back to access point, and there the association is complete. We'll talk about what is A nonce, S nonce, and MIC, and GTK later. Okay, the architecture of WAP is you have an autonomous access point. It is able to create, operate at that control, and data layers. Autonomous access points have switch-like intelligence. It has a thin access point. Switch-like intelligence is stripped out and relocated within a WLAN control device. The controller acts as a central administrator and control for several thin access points, considerably eases the administrative burden and managing many WAPs on a WLAN. So what's a wireless bridge? It acts as a distribution system service which translates traffic between an 82.11 device and the distribution medium used for backhaul. If the backhaul medium is wireless, WAP can also serve as a wireless bridge. The 82.11 standard discusses a mechanism called wireless distribution systems, whereby the frame format can handle 4 MAC addresses. Real-world deployments for WSR bridges with PTS and mesh network. Often used the wireless workgroup the wireless workgroup bridges often used when there are several non-wireless devices, such as Ethernet network PCs in a workgroup or in an office that require backup wirelessly connectivity to the network. Needed to provide resiliency in the event of a failed wire network or loss of service due to an router and switch failure. Performance can be quite bad. But without the use of wireless local bridge, some devices would have no connectivity at all. A home wireless router that acts as a gateway to the internet through a DSL or cable broadband connection or fiber. It typically has a built-in hub supporting four Ethernet connections and built-in WAP to create a WLAN. Provides internet connectivity to various devices connected via wired and wireless WLAN. For bring your device access, users should take the following steps. Implement a WPA2 protect encryption, set or limit the radio power, select access controls. The main difference between a residential and enterprise gateway is a matter of capabilities. Enterprise gateways typically have a WLAN interface, which connects to act as a translational bridge between two mediums. It's typically deployed as a guest point of access on the internet with no direct access to the corporate network. You have wireless antennas. They are either omnidirectional or semi-directional. Omnidirectional antennas are general-purpose antennas typically installed by default WAPs. They radiate radio waves equally in all directions, theoretically providing a 360-degree coverage. Semi-directional antennas are used when a coverage is required in a specific direction. RF radiance tend to be limited to 180 degrees. So this is an example of a Yagi antenna, which is a semi-directional. You also have a planar antenna. You also have a highly directional, very specific, comparable to a flasher with a highly focused beam, typically used in point-to-point situations where exact high gain beam is required. This is a grid antenna, which is a highly directional. You have parabolic, like salad dishes. You have multiple input and multiple output of MIMO antennas. They are newer technology. The architecture allows for multiple antennas to transmit and receive concurrently. MIMO technology allows complex signal processing techniques, provides enhanced range, throughput, and reliability. Key components in mobile 3G and 4G handset, but they also include in the 82.11n standards. So here's a Wi-Fi router with MIMO antennas. When dealing with antennas, it is important to understand antenna coverage charts from vendors, often called planar charts or radiation envelopes. Each antenna type has specific characteristics. So you have two perspectives on the coverage chart. A head-on azimuth horizontal aspect or a side-on elevation or vertical aspect. Here's the example of a horizontal, omnidirectional, or vertical. This is an azimuth, semi-directional, or elevation. So horizontal versus vertical. The site surveys that determine how RF radiation will behave in a facility takes into account coverage, interference, and gaps based on antenna placement and power consideration. Site survey process varies directly in its complexity, should include capacity planning and identify possible areas of interference. The spectrum analysis helps detect RF interference that might conflict the WLAN. Use a spectrum analyzer, a test device that measures the amplitude or frequency of radio waves. Spectrum analysis enables you to visualize and map what RF connectivity already exists within the 2.4 and 5.0 GHz spectrums. If background noise or unwanted radiation on those channels exceeds 85 dBm, wireless network performance suffers. And you could actually download a app from either Apple or Google that just scans the environment around you for spectral analysis. So, what are the source of noise interference? Microwave ovens, phones, fluorescent bulbs, elevator motors, Bluetooth radios, other 82.11 wireless networks, you have jammers, or you have microphones, or anything if it's a big area, or you have other audio video equipment. Coverage analysis conducts site coverage and capacity per individuals. Information gathered exercise to establish the capacity and coverage requirements based on the population density in certain areas, which may determine the need for smaller or larger cells or even collocation. Note special tools require an RF signal strength indicator on a laptop or other 802.11 enabled device. The access point placement. The site survey dictates location and boundaries access points. Position of each point must be checked to ensure it is within reach of wiring closet. Ethernet has a distance restriction of 100 meters with a Cat5 cabling. Use a mixture of omnidirectional and semi-directional antennas. After access points are placed and enabled, assessor covers both manually and through the use of predictive analytics. You have two modes of manual method, passive and active. In passive mode, a client card is to collect RF measurement of received signal levels, signal noise, and signal to noise ratios. In active mode, a client station authenticates and associates with access points, working at layer 1, 2, and 3. Use of predictive mode is a predictive modeling applications and simulation software to create visual models of RF surface coverage. A self-organizing WLAN is a new controller-based access point that provide ability to dynamically reconfigure lightweight thin access point based on changing RF conditions. Network can adjust signals, channels, power levels, and patterns to maintain optimal operating characteristics and network performance. So in this chapter, we talked about topologies and split of wireless, the standards of 82.11, how wireless access point approaches work, wireless antennas, wireless site surveys. Hope to see you guys in the next lecture.